Okay, here is our next video, Photoelectric Effect Part 2. This is made to go after Part 1. If you have not watched Part 1, please go back and do so now. All right, this Photoelectric Effect Part 2, right? We're looking at these, right, we've got a photoelectric effect, which is photons of light incident on some material. Doesn't really matter what it is, but we've got photons of light incident on some sort of material where electrons just pop out. So if we get, right, this photo or these light sources incident on whatever this material may be, maybe it gives the electron enough energy to escape. Okay. But before the electrons can escape, right, they need to have enough energy to do so. And here's your reminder: the kinetic energy maximum that an electron might have is whatever light was incident, the energy of the light incident, HF, minus this work function phi, right? That's the work function, which is how much energy it takes to escape the material. All right, this is conservation of energy. It's a statement of the conservation of energy. Whatever it gets out is whatever it got in minus whatever it took to escape. And that's how much energy the electron has once it leaves. All right. We were looking at this photoelectric effect, and I'll move this down because we were looking at this in the context of what if we have this in a capacitor, right? Parallel plates. In parallel plates where this one's positive, all that kind of stuff, and this one's negative, right? Because this will create an electric force to reverse the direction of the electron's movement. Okay, so if we're stopping the electrons, remember whatever this is going to be at some voltage. If this is at 0 volts, and that creates this stopping potential. The stopping potential is whatever electric potential difference it takes to stop the electrons. And right, we decided that whatever the kinetic energy was in electron volts, that is an equivalent number, whatever this number is the equivalent number to our stopping potential, which is just in volts. Okay, what if I take this now, instead of just looking at this as between parallel plates, right? Where do we get parallel plates? How can we make those? Well, I'm so glad you said a capacitor. All right, let's say that we have a circuit here. We've got a circuit with our parallel plate capacitor. All right, but maybe we've got a block of stuff here. And maybe, just maybe, right, this is our light incident on our block of stuff, whatever that might be. Okay, so we've got our little flashlight pointing down. Got our little flashlight pointing down here. Okay, because, right, this is the positive terminal of the battery. That's the negative terminal of the battery. So all the conventional current, right, shows the direction of positive charges. So that means that the positive charges will stack up on this plate. The negative charges will stack up over here. And as these electrons get released, right, they'll fly over, all of a sudden encounter the negatives, and they'll come right back. So they fly over, and then it comes right back. And then another electron's released, flies over, comes right back. That's the stopping potential, because what if, and I'll show this by erasing some of these negative charges, what if it's not strong enough to stop the electrons? Right, what's going to happen is this electron, oh, that's not the button I want it to click. This electron is now, instead of being stopped, this electron will go through, and if it's not strong enough, it will just create this current. All right, so the electron has this current here, and I might have this backwards here, because the electrons, the electron, it flies over, but if it hits the wire, all of a sudden, then we can get a current. Okay, I wanted to show this within the context of, and I will take this back to Google. I'll take this back to Google here, and if we Google FET photoelectric effect, this is one of the most spectacular FETs I think that they have ever created. It's absolutely wonderful. This one, they have not yet updated the programming code for it, so you still have to run like the browser compatible version, which um, less preferable, but you can run the Java version as well. If you want to run this, just make sure your computer downloads Java first, unless you're going to use this browser version. Essentially, though, this is what we have, right? We start at 0 intensity. If we increase the intensity here, oh, look at that. You've got electrons flowing around. Ah, nice. But what we can do, right? The battery, we can we can have the battery have voltage, right? And we flipped the battery over when it says -3, so the positive terminal's over here. All right, so we get a bunch of positive charges lined up on the battery on this side, a bunch of negative charges on this side. You can see that the electrons aren't making it very far. So the stopping potential stops them here, right about where my mouse is. That's as far as they go. Right, if you look closely, though, you can see some electrons don't make it quite that far. We've got some electrons that stop here. Every once in a while, there's an electron like that one. Oh, it stops way over here on the left, right? That's because of the different energy levels they start at, right? The maximum kinetic energy it can have comes from the electrons that are already pretty high up. They don't take a lot of energy to escape the atom, whereas the electrons that take more energy to escape the atom don't make it very far. So we can graphs current versus battery volt. I don't know if that's going to help us too much here. No, because this is just current. So I'm going to unshow all these graphs. But right, you can, and if we decrease the voltage of the battery, we'll get these electrons to go a little bit further. And hopefully we'll see the lines of right where the electrons stop. So you can see a couple of them are stopping right before the plate, as these ones are stopping right before the plate. There's a few that make it to the plate. Okay, so this is not enough voltage to make the stopping potential. You can see there's some lines where some electrons stop. Some of them are right in front of the plate. I've got some more that stop right about here. Oh, this one, both of these. Yep, they stop right about there. So there's another energy level. We might have some, here's a couple, some that stop right here. There's another energy level. Okay. Here's now the difference. Energy intensity. Oh, we can click this to show only the highest energy electrons. So this will be nice. This will help us. This will help us find that maximum kinetic energy. Okay, so once it's kind of cleared out, maximum kinetic energy, now we can see that all of these electrons are making it over to the battery. I'm going to change the battery's potential, though. And now let's see, where do these electrons make it? Oh, they only make it over here. Okay, so these electrons, they need more energy to make it to the other side. A couple ways we can do that. One, we can change the electric potential difference, right? So they would need less energy. Or we can actually give these electrons more energy and go into UV light. Okay, so now they're making it a little bit further than they were. Let's give it more energy here. All right, now these electrons are making it a good deal further than they used to. Let's see. Oh, not quite all the way. If we want to get the stopping potential, we want them to just barely make it to the other plate. All right, so that's for sure making it. We can probably decrease the energy a little bit, right? Decrease the energy, you increase the wavelength. Okay, so that's right between the two. Let's see, I'm not very good at... we need 285. Typed the wrong one. So 285 nanometers, maybe. Let's see. That's right, we want the wavelength where they just barely are absorbed. Oh, and those just barely are not. So what if we do 286? 286 nanometers. Let's see if those make it. 286, not oh, I went the wrong way. My apologies. Let's see about 284. All right, shorter wavelength, more energy. So if we have these 284, here's the first few from our 284 batch. Do they make it? Oh, they do. All right, so that tells us that for this material, we've got sodium. We've got sodium. 284 nanometers is the wavelength that we have incident on 2 volts of stopping potential. Okay, but 285 is where they actually stop. So that's the number we'll use. All right, so we say that delta V was 2.0 volts. We said our wavelength was where they just stopped, 285 nanometers. All right. Well, if we let's say, what is the work function? We could set up the problem. What is the work function? This is another thing that AP might have you work on. What is the work function of this material here? Or this what right, stopping potential is what we have. So we're looking for work function. They might also say binding energy. Binding energy is another term for that. All right, any of those things. But what is the work function, which means we are looking for phi? All right, well, we know from our equation, right, the kinetic energy max is equal to HF minus our work function. All right, we're looking for work function, so we can rearrange phi is equal to HF minus the maximum kinetic energy. All right, so HF, as a reminder, right, that's HC over lambda. The kinetic energy that it has, well, remember, this is our stopping potential here. That stopping potential turns into, right, energy is in electron volts, and it's the same number. So that's going to be our maximum kinetic energy will be 2 electron volts. Okay, so our phi, right, HC over lambda, that's 1240 EV nanometers over lambda. We got 285 nanometers. Okay, the nanometers cancel out. Minus 2 electron volts. Okay, if I take 1240 over 285, that spits out for me 4.35. 4.35. So I get 4.35 here minus 2, which if we do that, we get 2.35 electron volts. That is our work function for this material. All right, and that's just of whatever material it is that we have. I think we had sodium. Okay, so FET is just not updated for sodium to be the 2.75 that it was in the previous problem. But there we go. That's how you would find the work function of something. And FET just has the number wrong for sodium. At least according to Google, it has that number wrong. But there you go. Okay, that's how we can find work function. One thing that I will go back to on this, what should I call this? The simulation. That's the word. I'm going to come back to a color, and I'll decrease the stopping voltage. We'll go to some unknown. Oh, this is nice. They have an unknown here. Actually, we'll make the voltage be pretty high. You'll notice, right, I'm in blue even, and there's no electrons getting released. There are absolutely no electrons getting released, and these would be the highest energy electrons, so there's none. But we go into UV, oh, there's a couple of electrons, and I should maybe decrease my stopping voltage. So we get a couple of electrons being released, right? But I take my energy down, or I'm sorry, I increase my energy even more. Whoa, there's a few flying across. All right, so we increase our energy even more, and here we go. All right, you get more electrons flying across, as opposed to when we change our energy, when we decrease our energy by increasing the wavelength, there are none. There's absolutely none. Um, let's see. Let's try to get one of these with a low work function here, just so we can see a lot of electrons being released. Sodium might actually have the lowest of these all. Okay, well, you can actually see this, right? When we went from sodium, right? Sodium, they're making it all the way across, but when I click over to zinc, they don't make it all the way across. Okay, so that tells us that zinc, it requires more energy for an electron to escape from zinc than it does to escape from sodium, because sodium, it has more energy left over after it does the escaping. Okay, but what this shows us, right? The energy, or we'll call this the frequency, right? The frequency of light. The more we change the frequency, right? If I decrease my frequency by increasing the wavelength, if I decrease the frequency, it has less kinetic energy once it leaves. Eventually, it'll have no kinetic energy because there won't be any electrons escaping. There's still a few, but it has less kinetic energy to leave. Okay, we're in purple. Let's see if purple, yeah, there's still a couple leaving in purple, but there's less kinetic energy the more we increase our frequency. All right, so let's take a note of that. Let's take note of that. Okay, so in this photoelectric effect, right, we have K max is equal to HF minus R phi. Okay, here's our notes. As frequency increases, right, which means that wavelength decreases, then we get more kinetic energy. Opposite is true, right? As frequency decreases, that means we got longer wavelength. Kinetic energy would also decrease. Okay, there's something else that we can play with too, though, on this simulation. Another thing we can toggle back and forth, and that would be the intensity. Okay, so you can kind of see the electrons. You can see that they're going right about halfway, and there's a good chunk of them. What if, or if we count these electrons, what if I decrease my intensity? What does that do to the kinetic energy? Why not? I'll take it down to maybe 30-ish%. You can see more of a difference there. Okay, so I'm still getting electrons. They're still going right about halfway. Okay, so that means they have the same energy when they escape. So I change the intensity of the light, and they still have that same amount of energy, but what do you notice? There's less of them. There's less of them. And we could really see the difference here if I make this so that those electrons are flying all the way across. Okay, and you can see that I have current, right? We have non-zero current here. I get 0.317 amps as our current. Right? If we look at this equation, intensity is not part of this equation at all. So we can say as intensity increases, kinetic energy has no change. But what does happen is as intensity increases, there are more electrons released, right? Intensity is essentially just how many photons are there. And if you have more photons on this block of stuff, means more of them will get released. Okay, so at 30% intensity right now, I have 0.317 amps. What if I crank this up to, let's say 60% or thereabouts? Now I have 0.619 amps. What if I crank this up to 100% intensity? I have 1.042 amps. Okay, so this just means that the higher intensity it is, that doesn't change anything about the electrons. Right? It doesn't change anything about the electrons. Our stopping potential is still going to be pretty much the same. If we can find that stopping potential, it'll be a little bit less. Let's see if, a little less than 4.2. Let's see if we can do 4.1 volts. 4.1 volts, almost. Let's see if we can get just 4 volts. 4 volts almost. Anyway, so this might be like in the realm of 3.8 volts might be our stopping potential or thereabouts. Yeah, so that's getting pretty close. Okay. So we've got almost exactly at our stopping potential. If we change the intensity of light, right, if we decrease our intensity, the electrons, they still make it the same distance across. They still get stopped. All right, so this electron makes it out, it gets stopped, but then if I increase the intensity, the electrons, they don't go any further. They're not any faster. There's just more of them. I know it'll take it a little bit to warm up. So they don't go any further. Higher intensity doesn't mean they're faster, doesn't mean there's more energy. It just means there's more of them that have that energy. Okay. Those are things that AP does expect you to know, right? So as we change the frequency, the kinetic energy increases. And I should maybe call this Kmax. As we change frequency, kinetic energy changes. As we change intensity, kinetic energy does not change, but there are more electrons that get released. Okay, another thing that AP expects you to know, if we have this graph here, kinetic energy versus frequency. Kinetic energy versus frequency. All right, I'm going to put this back in the context of our equation. So I'll write this over here again. All right, kinetic energy max is equal to HF minus phi. Well, if this is our equation, right, that's on our y-axis. This is on our x-axis, so y equals, that means that h would be our slope, and b would be our work function, but it will be negative. So that means that we will get some sort of line that looks like this. Oh, but here's the question. Can we have negative kinetic energy? All right, kinetic energy is 1/2 mv squared. Mass can't be negative. V squared, it's a squared function, so that can't be negative. So we can't ever have a negative kinetic energy, which means that this whole portion of the line just can't exist. So a graph of kinetic energy versus frequency, and I'll take away the little shepherd's crook at the end. Actually, I should probably just erase the whole thing and redraw it. Kinetic energy versus frequency, since we can't have a negative kinetic energy, it just can't happen, right? That's what the graph looks like. Because we go off this y equals mx plus b form, which our b is a negative intercept based on this minus sign there. And our slope is equal to h, or Planck's constant. Well, this is actually how Planck calculated his constant, or one of the ways where we calculate it and can confirm that this is Planck's constant is the photoelectric effect, because we can measure the stopping potential. All right, stopping potential is the kinetic energy. Frequency, that's based on the wavelength. Work function, this is how we identify the work function of a bunch of different materials. And then the slope is going to be h, or Planck's constant. So that's what the graph of these things look like, right? Because there's some frequencies where there are just no electrons produced. And we can see that in the simulation, right? There's some frequencies. If I come over to this orangey yellow light and we let all the UV electrons die down, there we go. There's just no electrons produced. So we have to have some minimum frequency where these electrons can actually get produced. There's some minimum frequency where they can. And after that, the kinetic energy that they have is just on this linear slope with a slope of h, or Planck's constant. Okay, I've got a couple of quick practice problems for us here. First, practice problem. All right, we have, looking at this, we've got a circuit, right? Positive plate, negative plate, 2-volt potential difference. We've got some metal X, some metal Y. A photon with energy 4 electron volts is incident on metal X, which has a work function. Phi for X is 3 electron volts. Metal X is electrically connected to metal Y through a 2-volt power supply, that's already labeled, with the polarity shown in the figure above. All right, positives go this way, negatives go that way. So that means metal X will have a negative charge, metal Y will have this positive charge. What is the maximum kinetic energy an emitted electron could have when it reaches metal Y? Okay, right, so this is essentially, this conservation of energy problem, right? We know this. K max is HF minus the work function. Remember, this is the energy of the photon. That's why we say HF. But instead of giving us frequency or wavelength, they actually just give us the energy of the photon. So we have 4 minus, and then the work function of metal X is 3. So this means the maximum kinetic energy that an electron gets while it is emitted is 1 electron volt. All right, we're not done. Because it doesn't say when it's emitted. It doesn't say what's the maximum kinetic energy when emitted. It says when it reaches metal Y. So we need to look at what kinetic energy would an electron have over here, not right as it gets emitted. Well, if we take a look at this picture, we've got this electron and it's shooting over that way. This electron has a kinetic energy of 1 eV. All right, well, normally, right, we look at stopping potential. We look at when the electron stops. And this is a 2-volt difference. We've got a 1 electron volt electron. Does it make it over to the other side? My inclination at first is to say no, it doesn't. Because, right, it has 1 electron volt, but it would need 2 electron volts to make it through 2 volts of potential difference. Here's the difference, though. These are positive. These are negative. So that's why it's important to say the polarity shown in the figure. Because if this is a negative charge, it's going to take the negative of this electron and repel it. These positives are going to take the negative of the electron and attract it. So we have a force this way, an electric force that way. So we're not stopping the electron, we're actually speeding it up. Well, we start with 1 electron volt. And then it goes through this difference of 2 volts. 2 volts is the difference of delta V, right? Because that's a capacitor connected over here to this battery. And through Kirchhoff's loop rule, we know that whatever is gained has to be lost. So that's an electric potential difference of 2 volts. Okay, so if it starts with 1 and then it gets accelerated through 2 volts, right? We have 1 electron volt to start with, 1 eV to start with, and then we're giving it an extra 2 volts, but that's being applied to an electron, which means we're giving it 2 electron volts for a total of 3 electron volts. Answer C. And this is a publicly available AP question. So this is exactly how they would ask these questions. All right, so we decided, right, based on incident minus whatever it takes to escape, that the kinetic energy when it left metal X was 1 electron volt, which means the energy that it has when it gets over to metal Y, because of the polarity of the battery, it's accelerating the electron extra, so it gets up to 3 electron volts total, 1 plus 3. All right. Second question, which graph shows the maximum kinetic energy of the emitted electrons versus the frequency of light? Well, this is one we just talked about on the previous page, right? If we have maximum kinetic energy of the electrons, that means K versus frequency, right? There's some amounts of frequency for which there's no electrons emitted, so it stays at 0. And then there's some frequency where the electrons just barely get emitted. Then as we do that, the higher the energy the particle starts with, the more kinetic energy the electron will have to end with. So there we go. Answer A. If you just know the shape of this graph, you're doing great. And remember, slope equals h. And if we would backtrace this intercept, negative b is work function. All right, that'll do it for this video. I know these two were a little bit longer, so thanks for bearing with me through all this. There will be one more video following this on the last couple of concepts for modern physics, but that's all for this. If you have questions, let me know. Otherwise, I will see you next time.